In October 2025, a spacecraft orbiting Mars captured something that should be impossible, an object from another star system, moving at 129,000 miles per hour. It lost 4 billion tons of mass in days. The tail that physics demands should be there doesn't exist. 10 separate laws of nature, broken by one comet. Scientists calculated the odds of all these anomalies happening together in a single object. Less than 1 in 10,000. Maybe far less. This isn't speculation. This is measured data from multiple observatories. Something profoundly strange just passed through our solar system. And we only have one chance to understand it before it vanishes forever into the darkness between stars. What you're about to hear will challenge everything you thought you knew about what travels through space. October 3rd, 2025. China's Tianwen probe, orbiting Mars after completing its primary mission, tracked a faint speck of light 18 million miles away. This was humanity's closest look at Comet 3I Atlas, the third confirmed interstellar visitor ever detected. The challenge was immense. The probe's camera was designed to photograph Mars from close range, not to capture a dark, fast-moving object the size of Manhattan, traveling at 58 kilometers per second. That's 129,000 miles per hour. At that speed, you could circle Earth in 18 minutes. On November 5th, the Chinese National Space Administration released black and white images showing a blurry sphere surrounded by a fuzzy cloud. Scientists praised the technical achievement, but those who understood what they were looking at immediately recognized something was missing. There was no tail. When comets pass close to the Sun, they heat up. Frozen chemicals locked in ice for billions of years suddenly vaporize. The solar wind and radiation pressure push this material away from the Sun, creating the iconic tail. This is basic physics. The closer the approach, the more spectacular the display. 3I Atlas passed perihelion on October 30th, closer to the Sun than Earth's orbit. The heating was violent. NASA's Jet Propulsion Laboratory detected non-gravitational acceleration in the trajectory, meaning the comet was being pushed by its own outgassing. The math is definitive. To produce that force, 3I Atlas lost at least 13% of its total mass. For a comet weighing 30 billion tons, that's 4 billion tons of material ejected in days. 4 billion tons should create a massive visible tail streaming for millions of kilometers. But in the images, there's just a compact sphere. No tail, no streaming debris. Just silence where there should be chaos. This missing tail is the 10th documented irregularity. 10 separate behaviors that break patterns observed in thousands of comets. Each one rare on its own. All 10 together, the probability drops below 1 in 10,000, possibly 1 in 100,000. We're not claiming it's artificial, but based on verifiable data, something very strange just passed through our solar system. Let me walk you through all 10 anomalies. First, the trajectory alignment. Interstellar objects should arrive from random directions. Yet 3I Atlas's path is aligned with the ecliptic plane, where all our planets orbit, to within 5 degrees. It orbits retrograde, opposite to the planets, but precisely within the same flat disk. The probability of this happening by chance is 0.2%, 1 in 500. Second, the sunward jet. During July and August 2025, multiple observatories captured 3I Atlas shooting material toward the Sun. Not away, but toward. Solar radiation pressure should push all ejected material outward. Astronomers confirmed this wasn't an optical illusion. This was actual material defying the physics that should push it the other way. No conventional comet has ever displayed this behavior. Third, the mass and speed combination. 3I Atlas is 1 million times more massive than Oumuamua and 1,000 times more massive than Borisov, the previous interstellar visitors. It's also moving significantly faster than both. In interstellar space, large objects are rarer than small ones, and fast objects are rarer than slow ones. The probability of detecting an object that's both exceptionally large and exceptionally fast is less than 0.1%. Fourth, the timing and planetary encounters. In September, 3I Atlas flew close to Mars, perfect for observation by European Space Agency orbiters. Then it swung past Venus, later near Jupiter. Each encounter was close enough for detailed observation, but at perihelion, when the comet was brightest and most active, it was completely unobservable from Earth. The Sun was directly between us and the comet. It's as if someone planned a tour of major observation platforms while avoiding the planet with the most telescopes. The probability of this timing occurring naturally is 0.005%, 5 in 100,000. Fifth, the chemical composition. Spectroscopic analysis revealed unusually high nickel content, more nickel than iron, flipping the standard ratio seen in thousands of comets where iron dominates. The ratio of nickel to cyanide is orders of magnitude higher than any known comet, possibly factors of 10, 100, or even 1,000 times higher than Borisov. This isn't a slight variation. It's a completely different chemical signature. The probability of a natural comet displaying this composition is below 1%. Sixth, the missing water. Comets are famously dirty snowballs. Water ice typically makes up 70 to 80% of their mass. 3I Atlas contains only 4% water. This contradicts everything about comet formation. Comets form in cold outer regions where water ice is abundant. This object is more like a rock with slight frost. If you were designing something for an interstellar journey lasting millions of years, fragile ice that evaporates would be a poor choice. Rock and metal that endures would be better. Seventh, extreme negative polarization. When light reflects off surfaces, it becomes polarized. The degree of polarization reveals surface properties. Every comet ever observed shows consistent polarization signatures. 3I Atlas shows extreme negative polarization unprecedented in the entire database. The light reflecting from its surface doesn't match any natural dust grain models. The probability of this in a natural comet is below 1%. Eighth, the WOW signal alignment. In 1977, the famous WOW radio signal was detected from the direction of Sagittarius. It lasted 72 seconds and remains unexplained. 3I Atlas arrived from a direction coinciding with the WOW signal to within 9 degrees. The probability of random coincidence is 0.6%. While perhaps not meaningful alone, it adds to the stacking anomalies. Ninth, unprecedented brightness surge and colour. Near perihelion, 3I Atlas brightened faster than any comet in the observational database. The rate didn't match existing models. During this surge, the comet appeared bluer than the Sun. Normal comets reflect sunlight, appearing roughly the same colour or slightly redder. Blue comets are extraordinarily rare because no common mechanism selectively scatters blue light in typical dust grains. 10th, the missing tail we started with. The non-gravitational acceleration proves substantial mass loss. 4 billion tonnes left the surface. If it formed a dust tail, we'd see it. If it formed a gas tail, spectroscopic observations would detect it. Instead, there's a compact coma and no clear tail. The ejected mass simply vanished. 10 anomalies. Individually, conventional explanations exist for each. But when you multiply the probabilities, asking the chances that all 10 unlikely things happen together in the same object, the chance drops to below 1 in 10,000. This is where science meets mystery. This is productive discomfort. Harvard astrophysicist Avi Loeb noted that when something displays multiple independent anomalies, each unlikely on its own, we cannot ignore the pattern. The data doesn't fit natural comet models. Whether this object is a statistical extreme of natural formation or something more intentional, it compels us to expand our thinking. We must follow evidence wherever it leads, even if it challenges assumptions. The scientific community is divided. Some argue that 3I Atlas, while unusual, falls within natural variation. Space is vast. We've observed thousands of comets, but that's tiny compared to trillions that exist. Rare events happen. Statistical outliers exist. Perhaps 3I Atlas is the extreme tale of distribution, the 1 in 10,000 natural object that happens to be weird in multiple ways simultaneously. They argue for patience, for more data, for waiting until we encounter more interstellar visitors before drawing conclusions. Others argue that intellectual honesty requires considering all possibilities. When data doesn't fit natural models, when probabilities stack against conventional explanations, the scientific method demands expanding our hypothesis space. This doesn't mean abandoning rigor. It means following evidence wherever it leads, even to uncomfortable conclusions. The debate centers on interpretation, not data. The anomalies are documented. Multiple independent observatories confirm the findings. The question is what they mean. Are we witnessing the universe producing natural extremes we've never seen? Or are we confronting something that challenges our understanding of what's possible? The honest answer is, we don't know. We're living in the first generation capable of detecting interstellar objects. Before 2017, we'd never confirmed a single visitor from another star system. Then Oumuamua arrived in October 2017, detected by the Pan-STARRS telescope in Hawaii. It was the first confirmed interstellar object, small, elongated, tumbling, moving too fast to be bound to our Sun. It displayed unusual acceleration that couldn't be fully explained by outgassing. But it was gone before detailed study was possible. 2 years later, amateur astronomer Gennady Borisov discovered the second interstellar visitor using a telescope he built himself. Comet Borisov behaved much more normally. Clear coma, visible tail, spectroscopic signatures matching expected compositions. It seemed to confirm most interstellar visitors are normal natural objects. Then came 3I Atlas, detected in April 2024 by the Atlas Survey System in Hawaii, over a year before perihelion. The early detection gave astronomers time to plan observations and coordinate telescopes, but nothing prepared them for what the data revealed: 3 interstellar objects, 3 completely different profiles. The first bizarre, the second normal, the third bizarre in entirely new ways. Based on detection rates, astronomers estimate thousands of interstellar objects pass through our solar system yearly. Most are too small, too faint, or too far to detect. We only see ones that come close enough and are large enough to reflect sufficient sunlight. Our detection capability is improving rapidly. Within the next decade, we'll likely detect dozens. Within our lifetimes, perhaps hundreds. Each will teach us something about the galaxy beyond our solar system. But 3I Atlas will remain historically significant because it forced a question we weren't ready to ask. What if some of these objects aren't entirely natural? The idea sounds like science fiction. It triggers immediate skepticism, rightfully so. Extraordinary claims require extraordinary evidence. But science has confronted similarly uncomfortable questions before. When pulsars were discovered in 1967, their signals were so precise, astronomers briefly considered whether they might be artificial beacons. They even nicknamed the first pulsar LGM-1 for Little Green Men. Further study revealed a natural explanation: rapidly rotating neutron stars. But the initial openness to the artificial hypothesis was scientifically appropriate given the strangeness of data. Avi Loeb has been the most vocal proponent of taking anomalies seriously. His argument is straightforward. When multiple independent anomalies appear in the same object, when conventional explanations require stacking unlikely scenario upon unlikely scenario, intellectual honesty requires expanding the hypothesis space. He's not claiming proof, he's claiming the data warrants serious investigation of possibilities we've historically dismissed. His critics counter that nature is vast and surprising, capable of producing extremes we haven't catalogued. They argue for patience, for more data, for letting observation accumulation guide conclusions. Both perspectives are valuable. The tension between them is how science progresses. What's indisputable is that 3i Atlas doesn't fit our models. Whether that's because our models are incomplete or because the object is genuinely something we've never encountered remains to be determined. Future observations will help. As we detect more interstellar objects, we'll learn whether 3i Atlas is a unique outlier or part of a previously unrecognized population. The images captured by Tianwen 1 will likely remain the best we ever obtain. By January 2026, the comet will exit our solar system completely, returning to interstellar void. At that point, it will be too faint to track. It will disappear into darkness between stars, becoming once again just another invisible wanderer. We'll never see it again. This was our one opportunity to gather data, to photograph, to measure, to understand. The universe granted us a few months before reclaiming it. There are profound lessons here. First, humility. Despite powerful telescopes and sophisticated models, the universe remains fundamentally mysterious. We cannot predict what we'll discover next. Every time we think we've catalogued the full diversity of cosmic phenomena, something new appears. 3i Atlas continues that tradition. It arrived without warning, displayed behavior we didn't predict, and departed leaving more questions than answers. Second, the importance of observation. We only detected 3i Atlas because astronomers built survey systems scanning the sky continuously. The Atlas system wasn't looking for interstellar visitors. It was designed to detect potentially hazardous asteroids. But in cataloguing solar system objects, it found something from outside. This is how discovery often works. You build tools for one purpose and find something entirely different. Third, about perspective. 3i Atlas travelled for millions of years to reach us. It formed around another star, was ejected from its home system, and drifted through interstellar space longer than our species has existed. For a brief moment, measured in months, our paths crossed. We observed it. We measured it. Then it was gone, continuing a journey that will outlast every human alive today. That perspective is humbling. As 3i Atlas recedes into darkness, we're left with data, questions, and wonder. The data will be analysed for years, perhaps decades. New techniques will be applied, new theories tested, but the wonder persists. It's what drove ancient humans to track stars and what drives modern astronomers to study faint specks of light millions of miles away. Somewhere in the darkness between stars, other objects are travelling. Some we'll detect. Most we'll never see. But each one carries information about the galaxy. The search continues. The observations accumulate. The understanding deepens. And the universe, vast and strange, continues to reveal itself to those patient enough to look carefully at what it offers.